All right, Chemistry 3101. This is Chapter 3, Acids and Bases. In the first chapter, we did a review of general chemistry. In the second chapter, we looked at molecular representations, bond line structures, resonance structures, all that good stuff. And now we're going to switch gears and we're going to talk about acids and bases. And you might be wondering, hey, is this deja vu? You know, when I took general chemistry 2, I spent a lot of time talking about acids and bases and weak bases, of course. And yeah, I guess it will be a little bit of deja vu, but the reason that acids and bases are introduced in organic chemistry, you know, right at the beginning is because they play such a pivotal role in understanding reactivity. So in order for you to understand organic reactions, you have to understand acids and bases and understand them well. Now, if you go back to your general chemistry textbook, the first definition of acids and bases was put forth by Arrhenius. So you have Arrhenius, the Arrhenius acid. So Arrhenius said an acid is something that donates H plus. So an acid is something that produces a proton. And he said, okay, well, a base is something that donates hydroxide, OH minus. Now, acids that donate H plus. I mean, we can come up with Avogadro's number of examples, you know, sulfuric acid, H2SO4, HCl, you know, et cetera, et cetera. And when it comes to bases that donate hydroxide, I know you could come up with some good examples there too. What about sodium hydroxide or potassium hydroxide or lithium hydroxide? These are bases that come up all the time. But the problem with the Arrhenius definition is, where the problem with the Arrhenius definition of acids and bases is when we're talking about an Arrhenius base, because what if we have something like ammonia? Well, ammonia is in fact a base, but it doesn't possess a hydroxide. So we don't have a hydroxide in ammonia. So the Arrhenius definition of a base doesn't fit for a molecule like hydroxide. All right, well, let's move on from there and let's talk about a broader definition of acids and bases, and that is the Bronsted-Lowry definition of acids and bases. And so Bronsted and Lowry, they were able to, again, broaden the scope of the definition of an acid and a base, and we see how ammonia fits in this definition. And let me give you an example here. So the Bronsted-Lowry definition is just based on H+. It's just based on a proton. A proton is H+, okay? So the Bronsted-Lowry definition of an acid is that an acid donates a proton. Here's a classic example right down here at the bottom. HCl, it's an acid. If you put HCl in water, it's going to donate this proton, H+, to the water to form hydronium and chloride. So there you go. You see how the Bronsted-Lowry definition of an acid works. Now with a base, and I'm going to go back to the example of ammonia, what happens when we put ammonia in water is that the ammonia will accept a proton from the water to produce an ammonium ion, and it will also produce a hydroxide ion. And so we see how ammonia doesn't possess OH minus, but it produces it in solution. And so you can see how the broadened scope or the broadened definition of acids and bases, namely the Bronsted-Lowry definition, serves ammonia and explains why it is a base. Now, there is another definition of acids and bases, and that is the Lewis acid and Lewis base definition, and that's something that we'll touch on later on, and it will also come up later on in the class as well. So something to think about, the Lewis acid and Lewis base. Okay, anyhow, that's something for later on. So let's get back into our acids and bases. And you probably noticed that I had conjugate acid and conjugate base show up. Okay, so what's a conjugate acid and a conjugate base? Well, you need to know not only the definitions of an acid and a base, but you need to know the definition of a a conjugate acid and a conjugate base as well. So a conjugate base is a conjugate acid is what results when a base accepts a proton, and a conjugate base is what results when an acid gives up a proton. So on this slide, we're being asked to label the acid, the base, the conjugates in this reaction. So we want to label everything. Well, I'm starting out with this ion that has a negative charge, and I'm starting out with water. Now, if I look at my two products over here, hopefully it's pretty clear to see that the water ended up giving up this proton that's highlighted in red, right? The water donated a proton. So therefore, in this reaction, water is in fact behaving as an acid. Now, if we go with this definition right here, it says a conjugate base is what results when the acid gives up a proton. So when the acid loses that proton, highlighted in red, we end up with hydroxide, which is the conjugate base. So we get our conjugate base over here. Now, if we go back to our reactants again, you can see that this, what's called an alkoxide, this compound with a negative charge, that is behaving as a base, right? Because it is accepting a proton. How do I know that? It's got no proton here, but it's got one over here. So that means it accepted a proton. And if we go by, again, our definition, a conjugate acid is what results when a base accepts a proton. This must be our conjugate acid, like that. Now, you can memorize these definitions. There's nothing wrong with that. In fact, I recommend that you do. But if you ever get confused, if you're on a quiz and you're like, I'm not sure which one of these is the conjugate acid and which one is the base. Well, remember that the conjugate acid is called a conjugate acid because it's behaving as an acid, and the conjugate base is called a base because it's behaving as a base. So what you would want to do is you would just want to look at the reaction in the reverse direction. And let's examine what's going on here. If we look at this compound, you see what's happening when it's going from here to here, reverse, right? In reverse, it's losing a proton. It's giving up a proton. Therefore, it's pretty clear that it's behaving as an acid. Conversely, if we look at the hydroxide, if you're wondering, is it a conjugate acid or a conjugate base? Well, look what's happening to it when we go in the reverse direction. It's gaining a proton. And we know that Bronsted bases accept protons or are a proton acceptor. So either way you slice it, you're going to end up with the right answer. And you need to be able to discern an acid and a base, a conjugate acid and a conjugate base. Well, let's move on from there and see how we would examine a reaction like the one that we have here, something similar to it, in terms of curved arrows. So now we're really switching gears. And you're like, hey, Mr. Dion, I learned all about curved arrows in chapter 2 when we talked about resonance structures. Well, remember that resonance structures don't represent any real physical process. Okay, those are just used as tools to represent a resonance hybrid. Now what we're going to be doing is we're going to be using curved arrows in what? We're going to be using them in reactions. So now we're actually going to be showing the breaking of sigma bonds. And a curved arrow in a reaction shows the making and breaking of bonds involves electron movement. So we're showing the movement of electrons when we make and break bonds, okay? We used curved arrows to describe the flow of electron density. So let's take a look at what's going on here. We have this reaction here. Just kind of as an aside, in organic chemistry, when you see B with a minus like that, that's just kind of a generic, organic chemistry base, okay? We kind of lump all bases into this, into this B with a negative charge, and it has a lone pair, right? So the B could be, it could be hydroxide. Hydroxide has 3 lone pairs and it has a negative charge, right? So it could be any number of bases, but anyhow, we have our generic base, and then we have some kind of acid over here, right? We have HA. It could be HCl, it could be HBr, it could be HI, it could be H2SO4, whatever. Anyhow, we have a base and an acid. Okay, here's our generic acid. And what's happening here with these curved arrows is something different than what we saw with resonance structures. You see that the lone pair on the base is actually taking the proton. Let's stop for a second. If you're like, I'm confused about this, let's go back in our mind and say, what did we say a base was? According to the Bronsted-Lowry definition, a base is a proton acceptor. So it makes sense that the base is going to grab the proton, right? It also makes sense that the acid is going to lose the proton, okay? So if you're like, well, how does it lose the proton? Well, there are 2 electrons in this bond right here, and those 2 electrons are going to go on to the A, which is going to become the conjugate base, right? This is our conjugate acid, and this is our conjugate base, just using the same definitions that we looked at in section 3.1. And so it's important that you understand, and I'm going to draw these arrows again, or highlight them again, I should say. that this arrow right here, that arrow represents the formation of a bond, okay? This is a bond being formed, right? And that's this bond right here. How many electrons are in a bond? 2. Where did the 2 electrons come from? They came from the lone pair, okay? The second curved arrow, this one represents a bond being, or sorry, this one here represents a bond being broken. Okay, so we broke a bond, right? And we made a bond, formed a bond, right? Make a bond, break a bond, right? Anyhow, where did the pair of electrons from that bond go? They went onto the conjugate base, like that, okay? So this is actually representing a real bona fide reactions. Now, just to add more detail to what I just told you, it says here, they're the same kind of curved arrows that we used in resonance structures, right? I told you that whenever you see an arrow that's got a double head, it just represents the flow of 2 electrons. We use the same dang curved arrows for resonance structures. However, this is actually showing the physical movement of electrons, and it's what we call this an reaction mechanism. And learning to draw mechanisms is one of the most valuable skills that you're going to learn in this class. Okay, you're going to find that once we get to the second half of Chemistry 3101, we're going to look at so many mechanisms. Basically bombard you with different mechanisms. So it's important that you get these skills down pat right now. All right, that you learn how to draw mechanisms. Now, if you say, hey, I haven't mastered it in one day, well, Rome wasn't built in a day, right? It takes time to master drawing curved arrows, but you find that it's something that if you stick with, you will become proficient in drawing curved arrows. At first, it might seem a little bit like a foreign language or something, but just like a foreign language, you can become accustomed to it. Okay, very valuable skill, drawing reaction mechanisms. So let me just stop here for a second and explain something else. We're going to look at all kinds of reactions in this class. And unlike general chemistry, where you kind of look at A plus B gives you C, and maybe I'm simplifying a little bit, but in organic chemistry, we're actually going to dissect, step by step by step. Okay, how does this reaction work? If you think back to when you studied rate laws, reaction rate laws, now that might be a while ago for some of you, but that's probably one of the first chapters you would have learned in general chemistry 2, which is chemistry 1411 at UCCS. So when you learn about rate constants, one of the parts of that chapter that you would have studied would have been reaction mechanisms, and you talked about elementary reactions. Anyhow, if any of that jogs your memory, well, we're going to look at all those steps, those elementary steps, in a lot of detail in this class. Anyhow, I digress. Let's move on. Here's another specific example, and it's actually showing molecules, right? And a polyatomic ion here. So we have hydroxide, which is our base. And the acid that's shown here, this is acetic acid. So this is acetic acid. This is the major component, or one of the main components found in vinegar. Anyhow, and so we have our base, which is taking the proton from the acid to produce the conjugate acid and conjugate base. Okay, so let's go over a little bit of the vernacular here, the language that you're going to hear me use. The language that an organic chemist uses is she or he will say the base attacks the acid. You're like, what? It's attack? Yeah, we say that it's attacking it in this step here. It's attacking, and it's attacking the acid using the pair of electrons. The acid cannot lose its proton without a base taking it. Something you might not have thought about before is, going all the way back to your general chemistry. There's no exceptions to this rule. An acid cannot give up a proton unless there's a base to accept it. It doesn't happen, right? So the acid cannot lose its proton without a base accepting it. All acid-base reactions occur in one step, just like this. So these two arrows, these two steps actually occur simultaneously, okay? Both of these things happen at the same time. You make a bond and you break a bond, like this. The mechanism, again, shows 2 arrows, indicating that 2 pairs of electrons move simultaneously. And there you have it. So the base, again, attacks the acid, takes the proton. The acid donates a proton by breaking this bond, right? This oxygen here has 2 lone pairs. Now it's got 1, 2, 3, so it's going to have a negative charge. And there we have it, all right? Now we're just kind of getting warmed up here, but give me a thumbs up if you follow me. And if you have a question, feel free to chime in with that, because we're going to look at an example Does anybody follow me on the? Okay, cool, great. All right. Well, only one student. Okay, we got a couple of students to follow me. All right, good. Anyhow, look, I'm assuming, and I've taught this class for a long time, you know, that something that you're all kind of learning in organic chemistry, and I know you've seen this in other classes as well, but I'm sure that if I went around and asked all of you individually, I think that all of you probably, now that we're into the third week of class, you're starting to figure out that the best way for organic chemistry concepts to crystallize in your mind so that you fully understand them is to practice it, right? It's really the only way to get it, so to speak. All right, well, let's look at a practice problem. It's the first practice problem in chapter 3. It says all of the following acid-base reactions, well, there's only one of them here, that we will study in greater detail in the chapters to follow, okay? Our reactions that we're going to see. So this is a reaction we're going to see later on in the class, but we can still analyze it in terms of the mechanism and the acid, the base, the conjugate acid, and the conjugate base. The first thing I would do if I ran into a problem like this, the very first thing I would do is I would draw in all the lone pairs. Okay, so we're missing a bunch of lone pairs here. We're missing 2 lone pairs on this oxygen. We're missing 1, 2, 3 lone pairs on the hydroxide. We're missing 3 lone pairs on this anion, which is called a phenoxide. You don't have to know that now, but I like to throw words out there that you're going to hear later on. Okay, I'm going to ask my students, could anybody, if I circle this here, could anybody tell me, is this molecule behaving as an acid or a base in this problem? It's not a trick question.
Acid?
Absolutely, yeah, it's totally behaving as an acid, isn't it, right? Because, because it's donating a proton. Now you see it, now you don't, right? Here it has a proton, and it's like, where's my proton? Okay, so if it gave up a proton, right, donated H+, okay? So that's an acid. Ergo, this must be a base. Now you're like, oh, come on, Mr. Dan, you can do better than ergo. Yeah, I can, okay. Here it doesn't have a proton, and here it does. It accepted a proton, right? So that must be our base. So accepted H+. Now again, my trick for analyzing the conjugate acid and the conjugate base is I like to just think of the reaction in reverse and then think about what the hell is happening. You can see that this molecule is going from no proton to having a proton. So that must be the conjugate base. So here we have our conjugate base. In water, here is behaving as our conjugate acid. Now, something that you might notice, and you should know this from general chemistry, is that water is amphoteric, meaning that sometimes it behaves as an acid, sometimes it behaves as a base. It depends on the situation. All right, who nailed that one? I hope you all did. And let's try one more. We got a little bit of time here. I'm going to write one down here, and one that I just picked here. So if we draw this, did I not draw the curved arrows in the last one? Did I not do that? I was supposed to. Anyhow,
No, you didn't.
I didn't, did I? You know what, you guys? I can't be expected to keep track of all my wheelings and dealings, All right, well, let's try this one, then we'll go back and we'll draw some curved arrows. Anyhow, I'm just so excited to get started on some more problems with my students. Anyhow, I've gone ahead and drawn all the lone pairs in here. Let's do this one a little bit quicker. This is a hydronium ion, okay? That's behaving as an acid here, right? And then it donates a proton, and we're left over with water, which must be the conjugate base. This molecule here is acetone. That's basically nail polish remover. This acetone is behaving as a base, right? Because it's got no proton on the oxygen. Then it's got one here. It accepted a proton. And over here, we must have the conjugate acid. Now, I'm going to draw the curved arrows here. So if the base is going to accept a proton, we have to draw a curved arrow, and we're going to start on a pair of electrons. Remember, both of these bonds are intact, so the curved arrow must start on a lone pair, right? And pull off the proton like this. I didn't draw the lone pair on this oxygen, but now there's only one lone pair in the product, okay, in the conjugate acid. So this is the attack right here, where the base is attacking the acid. And look at the oxygen in water. Or sorry, look at the oxygen in hydronium. It's only got one lone pair, but over here, it's got two lone pairs. So where's that extra pair of electrons coming from? It's coming from the bond that's being broken like that. Okay, well, let's back up and go back to the question that I didn't answer fully, okay? It's asking us to draw the curved arrows here. So same rationale. Our base is going to attack the acid. So we'll draw a curved arrow from the lone pair. It doesn't matter which one you start on. Pick whichever one you like the most, okay? Something that you'll see if you're the kind of student who likes to peruse the internet, sometimes you'll see people draw it from the negative charge like that. That is actually technically incorrect, so don't do that. But we're going to start from a pair of electrons. We're making a bond, right? Okay, so this is the bond being made. This is the attack of the base on the proton. And then I'm going to show this bond being broken, right? And that pair of electrons is going to have to come over here in order to produce our conjugate base. All right, give me a thumbs up. Not if you understand it 100%, but if you're thinking, hey, you know what, Mr. Dion, lock me in a room with an organic chemistry textbook and some practice problems for a little while. I think I could figure it out. I think I could master this. All right, thanks, Brandon. Good. Okay. And it's going to take practice. There's just no way around it. But I promise you, and I don't promise anything, even on our wedding day, I told my wife this is a 3-year commitment. Okay. So I promise you that if you practice it, you will become proficient in it. Okay. It's just the way it is. You will master it if you work on it hard enough. All right. So here comes the dreaded Gen Chem 2 again. It's going to rear its ugly head a few times in this class. I won't even tell you that chapter 6 is basically all general chemistry too. But anyhow, you guys remember Equilibria? Remember equilibrium constants, KEQ? I know you studied that in general chemistry too. So let's review it a little bit here. And when we're talking about how strong an acid is, right? How do we quantify how strong an acid is? Is there a number that we can use to measure how strong an acid is? And the answer is yeah, we can actually use numbers to relate, to give us an idea about relative strengths of acids. Let me show you how you do that. So if I had, this equation here, if I have my acid, right, and I put it in water, it donates a proton to form hydronium and the conjugate base. Okay, if I was to measure K equilibrium like that, and again, this is something you learn in general chemistry too. Here's the equilibrium expression. So concentration of products to the power of their stoichiometric coefficients divided by the concentration of the reactants to the power of their stoichiometric coefficients. Well, if you look in our book, he basically states, kind of quickly, he says, we can eliminate the water because water has a relatively constant concentration of about 55.5 molar in any dilute solution, which is what we're going to look at in organic chemistry. And so we can simplify the expression to this, to Ka. So the equilibrium constant for our acid is equal to the concentration of hydronium times the concentration of the conjugate base divided by HA. And you're like, okay, that's great, Mr. Dion. That's wonderful. Thank you very much. Okay. But the question I want to ask you is this, okay? If the acid is strong, would Ka be bigger than 1 or smaller than 1? So if you had a strong acid, could anybody tell me, would Ka be large or small?
Ka would be large.
Exactly. It would be really large, right? Think about it. What's the purpose of an acid? The purpose of an acid is to donate protons. So the stronger the acid, right, the farther the equilibrium is going to lie to this side, to the product side. The farther the equilibrium lies to this side, the greater the numerator will be and the smaller the denominator will be. If you have a big number on top and a small number on the bottom, you end up with a number like this. If you reverse it, right, if you had a small number for the products and a big number for the reactants, then you'd end up with a number smaller than 1, right? So if we have a strong acid, then the Ka is going to be larger than 1, okay? The stronger the acid, all right? Here we go. So now if you're wondering, well, what about the numbers, Mr. Dion? Where are the numbers? You said we were going to quantify. Well, let's look at this in a little more detail. Okay, so if we go back again to just our generic reaction right here, what you're going to find is if you use this Ka expression, you end up with a very wide range of numbers. Okay, the Ka values are going to range from 10 to the -50. Who wants to keep track of all those zeros? Not this guy. Okay, all the way to 10 up to 10 to the power of 10. So that's 1 more 10. What is it? 10 times more than a billion, right? Anyhow, so you know, I'd be the first guy to lose track of all those zeros, right? Sign me up. I won't be able to keep track of all those. So since the numbers are going to be so small and so large, we have a workaround. Okay, so what we do is we take the minus log of the Ka, and that allows you to just focus on the exponent. So instead of being 10 to the power of 10, you get negative 10, and 10 to the negative 50, you get 50. And so what that means is that pKa values are going to range from, instead of 10 to the power positive 10 and 10 to the negative 50, they'll range from negative 10 to 50, which is much easier to wrap your head around, right? Okay, so the bottom line is that the lower the pKa, the stronger the acid. So if you have an acid, let's say with a pKa of -9, it's going to be stronger than an acid with a pKa of 1, right? The lower the number, the stronger the acid. Repeat that, okay? The lower the number, the stronger the acid. Now, I know you all can't wait to memorize stuff, so what I recommend you, let me just look at my notes here. You need to memorize not only that table, but you need to memorize, you need to memorize this table, okay? So let me just kind of go over the bullet points here, and then I'm going to switch to the next slide quickly. But it says there are more acids, well, there's no inside cover on an electronic textbook, but I think it's in the appendix. He has a pretty exhaustive list of acids and their pKa values. Each pKa unit represents a power of 10, right? So let's say you had sulfuric acid and you were comparing it to hydrochloric acid. Well, the pKa's are -9 and 7 respectively. So what's the difference? It's 2, right? What's the difference between -9 and -7? It's 2. 10 to the power of 2 is 100. And so sulfuric acid is 100 times stronger than hydrochloric acid. Now let me just switch gears here and show you this table. You need to memorize this table, okay? You need to memorize pKa values, okay? So here are all the acids, here are all the acids, and you need to memorize the pKa values of everything that's on this table. It's a big thing, you know, when I was a graduate student, we would memorize, you know, pages and pages of pKa's. They're just so handy, okay? So where's the formula for pKa? The pKa formula is right here. Just like pH is equal to minus log the concentration of H, pKa is minus log minus log of Ka. Anyhow, so let's take a look at some of these acids. Some of them are familiar to you, some of them maybe not as much, but let's just start at the top. If we see we have a really strong acid, this is sulfuric acid, right? This is H2SO4. It is one of the strongest acids that we would encounter in organic chemistry. It's got a pK of -9. It's really strong. Now, if we skip ahead to this one here, this is HCl hydrochloric acid, and we saw in the previous slide that HCl has a pKa of -7. Okay, but in between there, you're going to see this come up over and over in organic chemistry, a protonated carbonyl. Remember I told you a carbonyl is when you have a carbon doubly bound to an oxygen. So if you put a proton on that so that you have a positive charge like this, okay, that is something that's going to come up all the time. In fact, again, we drew that this morning, or we saw that in a problem this morning, the problem that I wrote down on the blank sheet, okay? So that's got a pK of -7.3, so that's strong as well. A hydronium has a pK of -1.74. Look, for this class, -2 will suffice. That's close enough. You can put it here, -2, like that. Oops. And the next one is acetic acid. It's a carboxylic acid. So carboxylic acid, all carboxylic acids that don't have any inductive effects, and I'll explain what that means later on, they have a pK of around 5-ish. So it says 4.75. This is called a 1,3 dicarbonyl. You have 1, 2, 3. You have a carbonyl here, so 1,3 dicarbonyl, right? 2 of them. Anyhow, those have a pK of around 9. Next, we have this molecule here that you're going to see come up a lot in organic chemistry. This is called phenol. The easy way to remember that is phenol ends with OL, right? Phenol, okay, instead of writing the, and it kind of looks like the number 10 in reverse, so the pK of a phenol is around 10. Water is 15.7. It's the only one that you're going to routinely see me actually list the pK value to the 10th position, so to 1 decimal place. Here we have, this is ethanol, just like the ethanol in a Coors Light, okay? Has a pK of 16, but you look at this, this is also an alcohol here. I know you all studied functional groups, and you see that it's got a lower pK. So you have 2 alcohols, and they differ by 2 log units, therefore 100 times difference in acidity, and we'll explain why that is later on. The next one, this is acetone. Okay, so this is acetone. And I mean, this is just a methyl group next to a carbonyl, or a CH3 next to a carbonyl. And that's around 19. This next one, this is acetylene, okay, which is an alkyne. And it's got a pK of 25. Next you have ammonia. I know you all know that. Ammonia, it's got a pK of 38. Sometimes you'll see it 36. It depends on the book. The next one is an alkene. So we have an alkene, and the vinylic hydrogen of an alkene is 44. And the last one is an alkane, okay, which has a pK of 50. Now, if you're like, well, hold on, Mr. Dion, you told me that -9 is really strong acid. Now, plus 50, that's got to be the weakest possible acid there is. And the answer is absolutely, absolutely. But what happens is, the stronger the acid is, the weaker its conjugate base will be. And the weaker the acid, the stronger its conjugate base will be. Okay, let me give an example. If you look at sulfuric acid, very common, very strong acid. If you look at its conjugate base, it's really weak. Okay, what does that mean? That means that it's weak. It doesn't want to pick up a proton, because that's what the definition of a base is. So that means if you have HSO4-, it's not going to want to pick up protons. It's really weak. And another way to say it would be this. What's the function of an acid? The function of an acid is to donate protons. So how is an acid going to be able to donate protons if the conjugate base isn't stable? Right? So another way of framing this would be to say, the stronger the acid, the more stable the conjugate base. Okay? The weaker the acid, the less stable the conjugate base. Okay? The weaker the acid, the stronger the conjugate base. So these are the kind of things you want to, sort out in your mind. Now, this next slide kind of summarizes that again. It's just a rehash of what I just told you, that, if you look at the pKa values, not only are they valuable to evaluate acid strength, but they're also useful to evaluate conjugate base strength, right? Very useful to do that. Okay, so again, the stronger the acid, the weaker the conjugate base, and the weaker the acid, the stronger the conjugate base. So if you're like, Mr. Dion, I studied general chemistry for a long time. I saw hydroxide show up as a base, I don't know, 10 million times in that class, but I never saw this. Probably not. But that is a base. We will see bases like this one show up in this class, and they will be, exceedingly strong. They'll just be really strong bases. And there are places for those in organic chemistry. Well, let's switch gears and try a practice problem. Is that switching gears? Not really. Let's take a look at a practice problem. This is propranolol. It's an antihypertensive. It says, using the table, identify the most acidic proton in the compound and indicate the approximate expected pKa. All right, one pKa that's not on that table, then a good instructor should always be thinking on his feet, right? Thinking of many things in his mind all at the same time. Anyhow, there's a pKa that's not in this table. I'm not going to ask you to memorize it for the next quiz, but if you have the proton on a benzene, so this is a benzene, right? And we talked about the resonance structures of benzene. It's got a pKa of around 43. I'll just throw that out there because I know that many of you have really inquiring minds. And if you're like, well, hey, Mr. Dion, it looks an awful lot like the vinylic proton in an alkene, it's pretty close. Yeah, it's very close, and for the same reasons, okay? Anyhow, can anybody just kind of figure this one out, or did anybody take a look at this one? And, I'm sure you all read the chapter with bated breath. Could anybody tell me what do you think might be the most acidic proton in this compound?
Is it the carbonyl acid?
So there's no carboxylic acid in here. A carboxylic acid is when we have a carbonyl with an OH bound to it like that. That's a carboxylic acid. Could anybody tell me the functional groups? Yeah, Byron has the answer, right? You have a hydroxyl here, right? You have an OH. Okay, this is an alcohol. Okay, an alcohol, right? If we go back to the table, and you have to flip around. I'm not insane, okay? I don't expect you to have these memorized right now. But you see that an alcohol, right? The two alcohols in here, have a pK of 16, 18, somewhere in that range. So even if you just wrote down a range, okay, even if you wrote down, we'll say the pK, let's say it's, somewhere between 16 and 18 probably because it's an alcohol, okay? And then here we have an amine, right? This is an amine. And if we go back to the table, okay, we saw that an amine, like ammonia, okay, has a nitrogen-hydrogen bond. It's got a pK of around 38, okay? So that means that this one's going to have a pK, amine pK, around 38, okay? Something like that. So close enough. Now, if you're like, what about all the other protons, Mr. Dion? There's tons of there's protons here, protons here, protons here. Well, those are all just CH2s, CHs, and CH3s, okay? So those are all just alkane or hydrocarbon. And if you go back here, a hydrocarbon has a really high pKa. So those are not acidic at all. Those are very, very weakly acidic. So we won't even consider those. We'll just eliminate those circles. And then if you look at all the ones that are on the aromatic, I told you that they have a pK of around 43. So you can see that there's a huge difference in pKa between an alcohol and an amine. An alcohol is around 16, let's say, or 18, whatever, and then an amine is around 38. That would be a difference of 10 to the power of 20, okay? So that tells you that an alcohol is a much, much more acidic, okay? Much more acidic, 10 to the power of 20. Would there be a pKa for the whole compound in this example? Yes, there would be a pKa for the entire compound in this example, but that is beyond the scope of our class. Okay, you'd have to evaluate several pKa's to do that. If you look at one of the medically speakings in our textbook, he talks about how drugs have a pKa. He mentions the pKa of aspirin and how it has a protonated form and an unprotonated form, and which form can cross the blood-brain barrier and cells and things like that. But for our class, Megan, all we're interested in is identifying, specific pKa's of these specific functional groups here, okay? So alcohol, much more acidic than an amine. Now, if you're wondering, what's your point, Mr. Dion? What's the whole point of all this? Sometimes it's nice to stop in a science class and ask, why the hell are we doing this? Like, why are you getting me to circle these functional groups and tell me which one is more acidic than another? What's our end game here? What's our goal? Our goal is eventually in this class to start looking at reactions, isn't it? Right? So if I was to give you a big old molecule like this and say, I'm going to treat this molecule with a base, you would have to be able to look at it and say, well, I know that this is definitely the most acidic proton in here. So if I treated this molecule with a base, this is the proton that would be donated, right? That's the proton that would be lost, so to speak. Okay? So that's kind of the rationale that you want to have. All right, well, let's take a look. And again, I do not expect you to have memorized the entire table, but it is helpful to do that. And I'm going to help you with this a little bit here. It says, identify the stronger base in each of the following cases. So look, if we draw a line here, there's A and then there's B below it. So let's look at A. So if these are bases, let's draw their conjugate acids. Okay, let's draw the conjugate acids of this. This is called acetylide, and this is called amide. Let's draw the, you know what, first let's draw in some lone pairs. What kind of hobo put these in here? Friends don't let friends leave lone pairs out. So let's draw the conjugate acid of this molecule, or this ion, I should say, would be acetylene. This is what it's called, acetylene. And the conjugate acid of this ion would be ammonia. Ammonia. Now, again, I don't expect you to have the whole table memorized, 10 minutes after I taught it or showed it to you, but I will expect you to know it on Monday for the quiz. The pK of acetylene is 25, and the pK of ammonia is 38. So which one of these is the stronger acid? The one with the lower pKa is the stronger acid. So this is the stronger acid, and this is the weaker acid, right? We could even write that in here. The ammonia is the weaker acid. And what do we know? We know that the weaker the acid, the stronger the base. So if the conjugate acid is the weaker acid, that means that this base is the stronger base. I'm going to give you a second to flip back to the table and see if you can figure out the answer to these ones here. Could tell me which one of these is the stronger base? I'll give you a second to think about it. If I labeled them, maybe if I label them 1 and 2, could anybody tell me which one would be the stronger base? Would it be 1 or 2?
2.
Okay. All right, we got a mixture of responses here, right? We have a heterogeneous mixture here. Okay. So I got a bunch of 1s, I got a 2. All right. Well, let's see if we can solve this one. And let's start by comparing the strengths of their conjugate acids, because when we look at a pKa table, pKa stands for acid. We're going to look at acids, right? We're not going to look at bases. Now, if you're wondering, hey, Mr. Dion, is there such thing as a pKb? Oh, you bet your Bobby socks there is such thing as a pKb. Okay, there's definitely a pKb. We will not be using pKbs in this class. If you want to look up pKbs and study it yourself, be my guest. But for introductory organic chemistry, I would wager that there is nobody or very few people in the world that teach pKbs in an introductory course. All right, well, anyhow, if we look up the pKs of these two alcohols, we saw that the pK of this alcohol was 18 and the pK of this alcohol is 16. So that means that the first one is the weaker acid. Therefore, this must be the stronger base. All right. So look, it's just a matter of comparing pKa's, nothing more than that. You have to go back to table 3.1, however you do it. Flashcards, maybe you write a little song about it, a nice rap tune, you know, you come up with all the pKa's in here, something that you can really sink your teeth in to. You make a good enough song, you know, you could probably post it to iTunes and monetize it and get rich, you know. All right, there we go. Well, let's talk about Equilibria even more. Okay. It says here that with the relevant pKa values, you can predict which direction an acid-base equilibrium will favor. Okay, let me ask you guys a question. Oh, jeepers. Let's see. The first time I ever taught organic chemistry at UCCS, I started with organic chemistry too. That was the first class that got me to teach. And I said to my students, I said, if you have a strong acid and if you have a weak acid, okay, keep in mind these are organic chemistry 2 students, you guys. They weren't where you guys are. These guys had already studied a whole semester of organic chemistry. And I said, you have a strong acid and a weak acid. Can you tell me, and this is to second semester students, could you tell me which side the equilibrium would lie to? Will it lie to the side of the strong acid or the weak acid? I'll just throw that out there to you guys. Could anybody tell me? Which side would it lie to? The answer's on the slide. It's going to lie to the side of the weaker acid, right? Absolutely. It would lie to the side of the weaker acid, right? So, Skylar, let me fix this up here. It's going to look like this. Look, it's not often that I do this because you guys don't want to see my face. You want to hear me talk about organic chemistry. That's what you're here for, right? But look, if we were in class right now, look, this is what I would say. Okay, you know what? The students could have knocked me over with a feather. They said, "Well, the equilibrium is going to lie to the side of the strong acid." I almost fainted. I said, "Whoa, whoa, 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 whoa! What the heck is the purpose of an acid? The purpose of an acid is to donate protons. You guys know this, making it rain, right? A strong acid is making it rain protons, right? A weak acid is only going to make it rain protons, right? Think about a strong person and a weak person. If I have a strong person and a weak person pushing against each other, which side is it going to lie to? It's going to lie to the side of the weak person, right? A strong acid is going to do its thing. It's going to donate protons. Okay, it's going to do what it's supposed to do. A weak acid is going to be like meh, meh. Okay, so it's going to lie to the side. It's going to lie to the side of the weak acid. Why? Because the strong acid performed its function. Anyhow, I hope that helps. Just me. Does that make some sense to my students? Now I know to some of you it makes sense. Does that clear it up for anyone? All right. Okay. Cha. Where are my students? Okay. No? Okay. All right. Well, I hope it clears it up for you. Anyhow, Ross says, yes, LOL. You know what, something, Ross? I just noticed for the first time, and I've been teaching with this iPad for, since March? And I just noticed that when I switch screens, that I could see the thumbs ups actually going on the, they were kind of flying up the screen. It was kind of interesting. Never noticed that before. Okay.
Yeah, I was gonna say, when you only think that like 2 or 3 people are giving you a thumbs up, everybody else has their thumbs up on their little bar down below.
See, I'm old. I got to learn these things, you guys. You got to explain this stuff to somebody like me, okay? Explain it. I'm like Michael Scott. Explain it to me like I'm a 5-year-old, right? Anyhow, let's go back here. That's embarrassing. Anyway, let's talk more about pKa values. Look, if you've got some pKa values memorized, look, you guys want to invest your time wisely. Let me tell you, if you memorize pKa values, again, I promise it will be worth your while. It will not be time wasted that you'll be saying, why the hell did I do that? Trust me, when you're taking organic chemistry 2, either in the summer or you started in August, for the fall semester, you'll be like, hot diggity damn, am I ever glad I memorized that? Okay. It will come in handy for the entire rest of the class. No time wasted, okay? Let's see here. What does it say? You can predict the direction of an equilibrium, right? Equilibrium is going to favor the side of the weaker acid. I just explained that. So if you had this reaction right here, look, you're on a quiz. You're just standing there, looking at a reaction. You're like, what the hell is going on, man? But look, if you had the pK of water memorized and the pK of this alcohol memorized, you can make a comparison right away and say, look, this is a weaker acid. The equilibrium is going to lie more to that side, just so quickly. And it's a beautiful thing to be able to do that, okay? All right, well, let's move on from there. Using pKa to analyze equilibria. Now, I wanted to say something else with this slide. Notice that this slide has an equilibrium arrow, right? You got the equilibrium arrow. Well, if you look at this equilibrium here, I mean, this is just psycho. Look at the difference between the pKa's of water and butane, okay? That's the one that has a pK of 50. I mean, that's 10 to the power of 34. That is such a high, that's such a big difference in the relative acidities that we just draw the arrow in one direction like that. Now, I know I have a lot of astute people who are listening to me right now, and they're saying, okay, Mr. Dion, what's the cutoff? What's the cutoff number, Mr. Dion? I need a number. It actually kind of depends, okay? I'm going to say probably for this chapter, maybe around 10, something like that would be the cutoff. So anything below 10, a difference in pKa units, you would draw equilibrium arrows, and anything above 10, you would draw a unidirectional arrow, okay? We draw the irreversible, what I call the unidirectional arrow. We draw an irreversible arrow because the reverse reaction, it's irrelevant in this case, okay? There's just such a big difference in pKa, okay? All right, well, let's get to it. There's something I really wanted to get to today, and that is the qualitative perspective, okay? You are going to love this, okay? This is something I didn't learn when I was a student. I kind of figured it out, but if you ever get on an exam and you freeze, that happens to people. I don't know if it happened to me, but maybe it's sometimes, you get just kind of nervous about something. You need to relax a little bit. Look, if you've forgotten a pKa, let's say, everybody forgets things, okay? There is a qualitative approach that you can take to just look at a molecule and start thinking about the structure of it, and you can evaluate a relative pKa, okay? Really cool. Let me show you how you do it. And this is something that was invented by the man himself, David Klein. He's the one, I'd never heard it presented this way. I studied organic chemistry for my entire adult life until I taught at UCCS and taught from this textbook. So you're really going to like it. Students really enjoy it. And let me show you how it works. It says, if you want to compare the relative strength of two acids without knowing pKa, so you've forgotten them, or maybe it's something that it's not even in the table. You just need to assess it, right? I'm going to ask you to solve problems, right? What you're going to do is you're going to compare the relative stability of the conjugate bases, right? Because remember, I told you probably 25 minutes ago, but I told you that the more stable a conjugate base is, that means it's a strong acid, right? The more stable the conjugate base is, the stronger the acid, okay? So in order to determine the stability of a conjugate base, we're actually looking at the stability of the lone pair, right? What's a conjugate base? HSO4 you know, this is just an example, right? We'd be evaluating the stability of, you know, the lone pair, right? If you had chloride, for example, that's a conjugate base of HCl, right? You're evaluating the stability of the lone pair. And let me show you how you do it, okay? Again, the more effective the conjugate base is at stabilizing that negative charge, that means it came from a strong acid, okay? And the four main factors that we're going to use to evaluate the stability of the negative charge are right here. Number one, let me get the black pen out here, the type of atom that the negative charge is on. Number two, if there's resonance contributors that we can take into consideration. Number three would be induction. And if you're not sure what induction is, if you understand electronegativity, I can explain induction to you very quickly. And number four, orbital, okay? And we talked all about orbitals in chapter one when we learned about sp, sp2, sp3 hybrid orbitals. So those things are going to come up, and we have atom, resonance, induction, and orbital. You put them all together, and you got this thing called aereo, okay? Aereo, and you have to remember that, okay? Remember aereo. It's going to come up, and I will actually use the acronym once in a while in the class. Again, it's nothing that I learned when I was a student, but I think it's really great. So let's take a look at the first one, the atom. The type of atom that carries the charge. Two rules, okay? If we were comparing these two conjugate bases right here, two beautiful conjugate bases, nothing wrong with these Lewis structures, they're just gorgeous, okay? But if we think about the negative charge on this and on this, what are these? These are carbon and oxygen. If we compare the negative charge, well, we're going to go by this rule here, which states that when we have atoms that are in the same period, right? If you look at the second period, and I don't expect you to memorize the entire table, you have boron, carbon, nitrogen, oxygen, fluorine like this. We know that since oxygen is closer to fluorine than carbon is, oxygen is more electronegative. So again, when we compare atoms in the same period, right? These are all from period 2. We use electronegativity to decide which one is going to better stabilize the negative charge. And so the answer is that this is a more stable conjugate base, therefore its conjugate acid would be stronger, right? If we drew the conjugate acid, this is a stronger acid than this. If you go back to the table, we said an alcohol has a pKa of around 16 to 18, somewhere in that range. And an alkane has a pKa of around 50. So yeah, that makes total sense. Now, I'm sorry that I put it in this order. This is kind of a goofy order because it's in reverse. It says here, the larger the atom, the more stable the negative charge. This only comes into play when we're talking about negative charges on elements in the same group. So same group. I should go back in and fix this. And this one here is in same period. Okay, so since, again, carbon and oxygen are in the same period, for this example, we're using rule 2. Let me show you how we would use rule 1. Yes, but Byron, okay? Since this is the one on the left would be a stronger base. Yes, absolutely, right? So this is stronger base, okay? Weaker base. Byron, close your eyes and just imagine this. Think about it. The more stable a base is, right? What's a base? A base is something that wants to take protons. If it's stable, it's like meh. Proton, it's indifferent to protons, right? It's like I don't give a crap about a proton. If you have a really strong base, it's going to be like gimme, right? Gimme protons. I want them, right? Because that's the function of a base. Weak base doesn't care about getting protons. So there we go. Anyhow, let's move on and I'll explain rule 1. And this is what I was getting to. If you were to compare water and hydrogen sulfide, so a little nomenclature practice here. So if you're to compare H2O versus H2S, okay? Now, if we draw the Lewis structures, you know the Lewis structures are very similar. This is water. This is hydrogen sulfide. Beautiful Lewis structures. If we draw their conjugate bases, here's the conjugate base of water. It's hydroxide. Here's the conjugate base of hydrogen sulfide. It's called hydrosulfide. Okay. So since we have a negative charge on a sulfur and an oxygen, sulfur and oxygen are in the same group, right? Same group. We use rule 1, the one that I had on the last slide. Okay, so now I'm talking about this rule. Okay, And now it's based on size. It's not based on electronegativity. It's based on size. And we know, this is going back to General Chemistry 1. Let's see here. We know that size increases as you go down a group. Okay? So since a sulfur is larger than an oxygen, the bigger the atom, the greater the ability it has to stabilize negative charge. Okay? So we'll put here, let's put it here. Larger atom. So sulfur is a larger atom than oxygen. Larger atom, therefore, weaker base. Okay, so this is going to be the weaker base. This is a smaller atom, and so it's going to be a stronger base. Now, if you wanted to just evaluate them in terms of pKa, I can prove it to you that this is 100% true, because the pKa of water is 15.7. The pKa of hydrogen sulfide wasn't in the table. I'll just tell you what it is. The pKa of hydrogen sulfide, and this is in the book, it's 7. So you can see that hydrogen sulfide is much more acidic, right? It's a lot more acidic than water, and therefore, if it's more acidic, its conjugate base should be weaker. So it's all coming together. Give me a thumbs up if you follow me on those two rules, even if I can't see the thumbs ups. Okay? All right. So again, the dominant effect when we're dealing with atoms in the same group is size, and the dominant effect when we're looking at atoms in the same period is electronegativity. All right, well, let's move on from there. So good. And let's take a look at the next one. Resonance. I told you that everything you learn in organic chemistry is for a good reason. If you're thinking, man, why did I spend so much time studying resonance? Well, here it is again. Surprise, okay? The next one, we go to area. So we go to the letter R, from A, atom, R, resonance. And if we had these two bases, okay? Here's a base, here's a base. We can't use atom. It doesn't work here because oxygen and oxygen are the exact same. So we have to go to the next thing, which is resonance. And what do we know about an anion that's got resonance? I'm trying to circle and I have the eraser selected. Anyhow, when we have resonance structures, as in the case here, the resonance structures do what? They serve to stabilize the ion. So since the charge is delocalized, or the structure has resonance structures, it's more stable, and therefore this is going to be a weaker base, and that tells me that its conjugate acid must be stronger, right? Let's draw the conjugate acids of both of these. The conjugate acid of this base would be ethanol, and the conjugate acid of this, I'll just draw the conjugate acid of this, is acetic acid. If you go back into your table, you'll see that the pK of ethanol is around 16, and the pK of acetic acid was 4.75. We'll just put 5. It's close enough. So again, you see that this is a stronger acid, so it makes sense that this is a weaker base. So you've got to, and if you're like, well, which one do I use? Both. Use both, my friend. Use every tool that you have at your disposal to get a good grade, okay? If you hide things in your brain, I'm not going to penalize you for that, okay? That's called knowledge, okay? If you memorize the pKa's and you learn aereo and you got both of them at your disposal, hey, you're rock solid, right? Okay, there we go. Give me a thumbs up if you follow me on resonance. I can only see one thumb at a time, I think, but there we go. Okay, let's move on and let's talk about the next one, which is induction. You guys remember electronegativity? I say there's, you know, they say that there's only 2 absolutes in life, right? Death and taxes. I say there's 3. There's death, there's taxes, and students love electronegativity. I'd say I teach general chemistry basically every semester, and students, it seems to me that, and I don't blame them, that their favorite periodic trend is electronegativity. You guys remember that when we have the periodic table, right, and we looked at this already today, so I'm kind of repeating myself, that electronegativity increases, right, in this direction, going across a period and up a group until you get to fluorine, which is the most electronegative element in the periodic table. Now, induction is this, okay? If we can't use the atom, that doesn't work. If we can't use resonance to decide which is the more stable base, we look at induction, because induction can also stabilize a formal charge by spreading it out. Now, how is induction different from resonance? Well, induction is the result of having electron withdrawing groups or atoms that pull electron density away from their surroundings. And what they do is they end up stabilizing a negative charge. Let me show you what I mean. If we draw the conjugate base of these two molecules, we have acetic acid and trichloroacetic acid. Let's draw their conjugate bases. I got to try to remember to leave all my lone pairs in. I've been teaching organic 2 for too long. You know, you get lazy after a while. There we go. So we draw all these chlorine, chlorine, chlorine. Okay. Chlorine is just below fluorine in the periodic table. Chlorine has an electronegativity of around 3.0. That's its electronegativity, roughly. Okay, so if we look at, let's examine the negative charge on this oxygen, the negative charge on this oxygen. We can't use A. We can't use atom because the negative charge is on an oxygen in both cases. That doesn't work. We can't use resonance because we can draw the exact same resonance contributors for both of these, right? I could draw this resonance contributor and I can draw this resonance contributor. So we can't use resonance to solve the problem. Okay, so let's delete those. We go next to induction. We have all this negative charge on this side of the molecule. The reason why the trichloroacetic acid is more acidic is because since chlorine is more electronegative than carbon, it's going to have a dipole going this way, right, on all of these bonds. These are polar bonds. And what that does is it sucks some of this electron density away from the oxygen and further stabilizes it. It's very conceptual, right? But what would be the effect if I had, you know, instead of 3 chlorines, if I only had 1 chlorine? Well, let's take a look. If you go from acetic acid and then you add 1 chlorine, you see that the pKa drops because the chlorine has a dipole, right? It sucks electron density away from the negative charge. Now, the conjugate bases aren't drawn here, but you have to imagine it, right? If we add more chlorines, right, it just sucks more and more electron density away. And so the more electron withdrawing groups you have that can stabilize that negative charge, the more acidic it becomes. Give me a thumbs up if that makes sense. And while you're doing that, I'm going to draw something here for you. Let me get the eraser over here. Okay. Jeepers. Come on. There we go. All right. So I have a question for you guys. It's not a question that I had planned. But you see these 2 compounds here that I have inside the yellow box on the far right? I'm going to label them, you know, compound 1 and compound 2. Could anybody tell me which one would be a stronger acid? Would it be compound 1 or compound 2? Who's got some intuition?
Compound 2?
Absolutely. Yeah, absolutely. Okay, compound 2 is going to be a stronger acid. In fact, compound 2 is called trifluoroacetic acid. It's got a pK of 0.23. Why? Because fluorine has an electronegativity of 4.0 and chlorine is only 3.0. So therefore the dipoles here are stronger, right? They're stronger than the dipoles on the chlorine. And so they stabilize the conjugate base even more. All right. Byron, you're saying something about an oxygen gaining a partial positive charge. That's not happening at all. Okay. That is not happening. It's not pushing hydrogen away. Anyhow. All right, there we go. So we covered atom, induction, resonance, and we have one left, and that is orbital. Really, this is what we call scraping the scraping the bottom of the barrel, right? If you've exhausted all of your ideas, atom doesn't work, resonance doesn't work, induction doesn't work, then you got to examine the type of orbital. And that's why it was so important that you understood steric number, hybridization, right? Because you got to recognize an sp3, an sp2, and an sp hybridized atom. Well, let's think about the size of these orbitals. If we have an sp3 orbital, and I went over this in chapter 1, it's 25% s and it's 75% p. A p is bigger than an s, so it stands to reason that an sp2 is going to be smaller than an sp3 because it's 33% s and 66% P. And over here, it's 50-50, right? 50-50 S, or sorry, 50% S and 50% P. So the idea is that the orbitals get smaller and smaller as we go from sp3 to sp2 to sp. And you're like, okay, Mr. Dion, I get it. I understand orbital size. You went over that in the first chapter. What's that got to do with the stabilization of a conjugate base? And the answer is shown right here. Okay. Did I not write it on here? Yeah, here we go. Okay, sorry. It's right here. Here's the answer. The closer the electrons are held to the nucleus, the more stable they are. So if you're like, well, does that mean if I have electrons in an sp orbital, hybrid orbital, they're going to be more stable than electrons in an sp3? Yep, because it's smaller. Okay, so all you have to know is the relative size. The smaller the orbital, the more stable the conjugate base, just because the electrons are held tighter to the nucleus, right? A nucleus is positive, stabilizes a positive charge. Nothing more than that, my friends. Nothing more than that. Look, if I was to ask you to compare the relative acidities of these three compounds, ethane, ethylene, and acetylene, right? If we examine, a proton in each one of these and we remove them and we draw the conjugate base, and it's going to take me a while to do that, but I'll do the fastest I can. There we go. So we have this conjugate base. We have this conjugate base. And we have this conjugate base. Now, if this is the strongest acid, that tells me that this is the most stable conjugate base. And it tells me that this is the least stable conjugate base, okay, because it's got the highest pKa. It's the weakest acid, okay? So just talking about stability. And the reason that this one is the most stable is because the lone pair here is on an sp hybridized orbital. The lone pair here is in an sp2 hybridized orbital, and the lone pair here is in an sp3, right? That's all there is to it. So I see that you guys really want me to talk about base strength, right? So if this is the least stable conjugate base, least stable, it means it's the strongest base, and this one will be the weakest. You are the weakest base, right? Like that. And that's all there is to it, my friends. Area. So it might be something to think about in the last few minutes of lecture. Now, again, we have a lecture on Friday where we're going to be able to wrap up the rest of the material. But yeah, and we're going to look at the last few sections. Yeah, we'll be able to get through it, no problem. I just want to mention one thing before we kind of wrap up today's lecture. And that's the Aereo is not, it's a great tool, okay? But it's not 100% accurate. There are situations where it's not going to be 100% reliable. And now if you're like, oh, dang it, I was depending on that versus the pKa's. Now, I told you have to memorize table 3.1, right? You have to memorize all those pKa's and use Aereo, right? Organic chemistry is a class where you're going to use every tool at your disposal to help you solve problems. You take every bit of knowledge you have and you throw it at it and you figure it out, right? Now, let me show you an example where Aereo doesn't work. And this is a very specific example. I know you all read the textbook before coming to class. One of the best textbooks in the world, right? But this is a really specific example, and it will come up a couple times in the class. So you should know this example that's on this slide, and it's this one right here, okay? If you compare the pKa, the relative pKa's of this molecule and this molecule, so these are acetylene and ammonia, you can see that ammonia is a weaker acid, and so the equilibrium is going to lie to the side of the weaker acid. And we could say that because we know the pKa values. However, if we had tried to just use Aereo, okay, if we had tried to just slice it by Aereo, what would we have said? We would have said, okay, well, over here we get a negative charge on a nitrogen. Here we have a negative charge on a carbon. If you look at the second period, it goes boron, carbon, nitrogen, oxygen, fluorine. Well, hey, nitrogen is more electronegative. Therefore, this must be the more stable base, and the equilibrium should lie to that side. But it's not true in this case. Okay? Now, if you're like, well, shoot, Mr. Dion, why do you do this? You know, why are you doing this? Well, first of all, I didn't do it. It's just nature. Okay? But again, this is a very specific example, but I just want you to, you know, kind of keep this thing in mind moving forward. Okay? Is that something, again, that I hope you're learning in organic chemistry, is that if you go back to general chemistry, there was usually, and I'm trying to think of exceptions off the top of my head, and I can't think of any right now, but usually in general chemistry, everything was just a hard and fast rule. You just stick to the rules and that's it. Well, what you'll find in organic chemistry is that it's not always like that. Now, if you're like, well, then that means I'm not going to be able to solve some of the problems. No, I'm always going to give you problems that you're able to solve. Okay, I'm never going to split hairs so that I'll ask you something that you won't be able to solve it with the knowledge you'll have. Okay, you'll always be able to solve the problem applying the knowledge that you have. Okay, so what I want you guys to do before next class is be sure to read the remainder of the chapter if you haven't done so already. Again, and I won't keep saying this every lecture, but just as a reminder, I highly recommend reading the chapter before coming to class. I was where you are at one point, right? I was an organic chemistry student in 1995, and I can tell you that it's very difficult to learn organic chemistry just by listening to your instructor. Okay, I don't think it's the best way to do it. Maybe some people just, you know, love the sound of my voice and they're like, I learned everything from Mr. Dion. Well, I would recommend that you read the book first, and then kind of when you come to class, it'll help to fill in the blanks. You know, it's analogous to come into class without having read the textbook. It's kind of like jumping into ice cold water. You know, you can swim around in ice cold water when you jump in it, but it's not comfortable. You know, whereas if you've read the textbook, you're a little bit familiar with everything, even if you don't know it all, which I wouldn't expect you to. Then you come to class, Mr. Dion can just kind of clarify things for you and you know, help you to see things a little more clearly. Okay, so what we're going to do here is next class, we're going to start with this practice, the skill, and we're going to evaluate the relative acidity of the protons in red and the protons in blue. All righty, here we go.